but you're here, I'm here, and therefore, guess what? It's time to start. All right, welcome to another exciting afternoon of chemistry with your host, me, Dr. White, and Chem 170. All right, first of all, important public service announcement. If you haven't done it already, get your flu shot. I got mine on Monday after class because I would have gotten it last week, but they ran out of the super or high potency flu shot for people like me who are over 65. Oops. But anyways, important for you to get it. Why? About 2-3 years ago, I didn't get flu shots. I don't need that. Well, I came down with the flu. It got worse, worse, worse. I went to my doctor because it was getting really worse, and he put on my finger one of those devices that measures the oxygen level in your blood. By the way, that's due to chemistry. They know how to do that. And he looked at the number and said, I'm going to try some inhalation therapy right now in my office. And if this number doesn't go up, I'm sending you to the emergency room of the hospital right now. Luckily, it went up, but I was still quite sick for a while. And after that, I learned my lesson, get your flu shot, because it can get quite nasty. All right, today I promised that I would go through first the alcohol problem set. We'll do aldehydes and ketones, my favorite, and then we'll do the lab today, which is electrophilic aromatic substitution, or how to put a nitro group on a benzene ring. So let's get started. Everybody see the alcohol problem set on your screen? Can you see it? Okay, thank you. Zoom continually, I'm not the only one. You think it's on the screen, it tells you on the screen, the students tell you it's not. All right, let's get going. Remember, I'd like to do one on each page. I do one page at a time. If you got any questions, fire away. And the first one is, give the IUPAC name for the following. Well, let me remind you, alcohols that, I'm going to go to my whiteboard because it's almost impossible to write on a remember, alcohols, find the longest chain of ring, name it as an alkane, drop the E, and add OL at the end. For acyclic, meaning not in a ring, you need a number. Which carbon has the hydroxyl group on it? For rings, no number, because the carbon with the hydroxyl group is always number 1. So now that we know that, and you know that, let's get back to our problem set. And if we look here, what do we have? 3 carbons, propane, alcohol. Remember, look for what's different. What's not carbon, what's not hydrogen, should get your attention like that. And this is an alcohol, so propane becomes propanol, but what carbon is it on? It's on carbon 1. Remember, the carbon with the hydroxyl group always gets the lowest number. And if we go to C, again, what do we have? What's different? Ooh, hydroxyl group on a carbon, alcohol. How many carbons is the longest chain with the carbon with the hydroxyl group? 1, 2, 3, 4, 5, pentane. Drop the E, add OL, pentanol. What carbon is it on? You start from this side, 1, 2, 1, 2, 3, 4. That should get the lowest number. I hope you all agree 2 is smaller than 4. Therefore, it's 2-propanol. Oh, look, it's your good friend, the methyl group, and it's on carbon 3. Now, if we look at this ring, oops, get back here. We have a hydroxyl group on a carbon. It's in a ring. How many carbons count each bend? 5. Pentane, ring, cyclopentane, alcohol, drop the E, cyclopentanol. This carbon is going to be number 1. Therefore, I don't put a number here, just like I didn't do up here. And then I have an isopropyl group and a methyl group. If this is 1, you count or number in the direction clockwise or counterclockwise that will give the alkyl groups the lowest number, and that's clockwise 2 and 3. The methyl group is on 3, isopropyl on 2. Now, this is the correct IUPAC name for that. If you put down 2-isopropyl, 3-methyl cyclopentanol, I'd still give you full credit. Shh, don't tell anybody I'm being nice. It'll ruin my image around here. All right, there are 2 types of nomenclature or naming questions. And that one is, here's the structure, give the IUPAC name. The other is, here's the name, IUPAC, or now common name, draw the structure. And how do you do that? You start from the right and move left. And if we look at A, OL tells me alcohol. If that were an E, pentane, 5 carbons, and it's on carbon 2. So this is 1, this is 2. You could have counted here 1 and 2, but I better warn you about something about Dr. White, me. And that is from here to the next couple of chapters, I learn, and good habits I don't break, for these type of molecules, functional groups, we start when we're drawing it from the right, 1, 2. But if you start here, 1, 2, I still will give you full credit. So this is 2-pentanol. If we look here, cyclobutanol, OL ending, drop the OL, add E, cyclobutane, 4-membered ring. Remember, I'm an organic chemist. This is a ring. No, it's not a square. This is organic chemistry. And any carbon you put the hydroxyl group would be right. Ooh, this is a good one, C. Start from the right, move left. OL ending, alcohol. If I put an E there, octane, 8 carbons. Where's my hydroxyl group on carbon 2? You could have started from this end, but Dr. White doesn't. But you can on a test, it's fully correct. Then on carbon 3 and 5, diamines 2, methyl, you know, CH3, and here's how you do it. Oh, look, let's do D. And that's phenol, or para-isopropyl phenol. Phenol, OL tells you it's an alcohol in this case, but phenol is a benzene ring, don't forget the bonds, with the hydroxyl group, and in the pair position 1, 4, you have an isopropyl. You'll start seeing sometimes when I'm drawing rings, I'll do the full line structure. I stay away from this for this class, but for my colleagues being lazy, if I were talking to other PhDs, I'd probably write it this way. A couple of years ago, students asked, well, that's on the internet. Can you show us that way too? And I started to. Now, if we look at F, 3-isopropyl cyclopentanol, OL ending, alcohol. If that were an E, cyclopentane, 5-carbon ring. It's got a hydroxyl group. I put it here. You could put it on any carbon. All you're just doing is rotating the ring. And then on carbon 3 is an isopropyl. 1, 2, 3. All right. And this one, 2-methyl-2-propanol, OL ending, alcohol, propane, E, 3 carbons. The hydroxyl group is on carbon 2, and there's a methyl group. Now the common name, and I never asked you what's the common name of the structure, but I could have also asked, draw the structure for T-butyl alcohol. This would be the same T-butyl group with a hydroxyl group. All right, now on test number 2, there'll be 3 types of questions: general knowledge, and then there'll also be nomenclature and reactions. Nomenclature, we just did the 2 types of problems. That would be nomenclature. And now let's look at some reactions. Give the product or products. By the way, I'll have usually 3 synthesis problems. Now, if you notice, I don't have any synthesis problems in the practice problem. Well, you can take any one of these, you have the answer, cover this part, and figure out what would I put there. And you've got your synthesis problems. All right, how do you make an alcohol? Well, this is the only reaction that was on test 1. I can put on test 2 also. And that is this reaction. What's different? Double bond, acid and water. Think of water as HOH. You break the pi bond, one carbon gets H, the other gets OH, and it follows Markovnikov rule. And here, this has 2 hydrogens, this has 1 hydrogen here, hydroxyl. Do you break carbon-carbon single bonds? No, you don't. So I have 4 across, 4 across. This carbon gets the hydroxyl, this gets the hydrogen. Ooh, rings. Mother Nature and Dr. White love ring students down. Same reaction. What's different here? Double bond. What are we reacting with? Acid and water, HOH. And what happens? One carbon double bond gets the H from water, the other gets the hydroxyl, OH. How do you know? Markovnikov rule. Oh, wait, you got to figure out how many hydrogens are in each carbon of the double bond. Don't forget, there are 4 bonds to carbon. Hold on. Don't forget, there are 4 bonds to carbon. And therefore, if you count the bonds, there are 4. Therefore, there's 0 hydrogens there. Remember, on a ring, we don't show hydrogens, but they're there. And this one has 3 bonds, so there's 1, which smaller number, or which the larger number, 1. So the hydrogen goes there, hydroxyl goes there. If you put the methyl here and OH there, that's correct. Remember, this methyl group comes along for the ride because you don't break carbon-carbon single bonds. All right, D, E, and F are the same reactions. Let's look at F. I have what's different. Ooh, hydroxyl group on a carbon, alcohol. I'm reacting with sulfuric acid, H2SO4, heat, and it's high heat. That's what the 180 tells you. And the general reaction up here is alcohol, which has an adjacent carbon with a hydrogen. Adjacent means next door, bonded to that carbon with the hydroxyl group. Acid and heat, you lose water and form a double bond and follow Zays's rule. Zays's rule is you get the double bond that has the most carbon atoms directly bonded to the carbons of the double bond. I'll say it again. Zays's rule is you get the double bond or the alkene that has the most carbon atoms. Key here is directly bonded to the carbons of double bond. So if we look at F, here's my hydroxyl group, and I have adjacent carbon here that has the hydrogens, which I labeled A. And to this side, here's my carbon with the hydroxyl group. I have hydrogens labeled B. You could also do this methyl group, but this and this would be identical product. So I only did 1. So if I lose the hydrogen from A and the hydroxyl group between the carbon with the hydroxyl group and A, I'll form a double bond. You get this compound Remember, you don't break carbon-carbon single bonds. Now, if I lose the hydroxyl group and a hydrogen from B, you get this compound. Again, excuse me, the methyl group is still there for the ride. Now, which one is the actual product you get? Well, you count the carbon atoms directly bonded to the carbons of the double bond. And if you notice, I have in compound A, these two carbons circle because they're bonded to the carbons of the double bond, 2. In B, here's my 2 carbons double bond, and we have 1, 2, 3. Remember, directly bonded, you don't count this one. So this has 2 carbons, this has 3, which is a higher number. B, Zayseth's rule says that's what you get. And that's how you, ooh, I played a joke on you people in E. How many bonds to carbon? 4. Therefore, here's a hydroxyl group in a ring. I have these 2 adjacent carbons. If I look up here, it's got hydrogens, 2 of them. If I look at this one, no hydrogens. So you don't have to worry about Zayseth's rule because the only place you can form a double bond is here. Next is you learn what ketones, what I showed you at first in alcohols. If I have a hydroxyl group on a carbon and oxidize it, I'll get a ketone or an aldehyde. This is a secondary alcohol plus oxidizing agent, you form a ketone, carbon-oxygen double bond. Same thing here, secondary alcohol. And here I have a primary alcohol. Carbon with a hydroxyl group oxidizes. It's a primary, you form a carbon-oxygen double bond. And here's one way of writing it. If you brought the hydrogen up there, you could. All right, next reactions. I have 3 of them. Oh, let's do K. What's different? Hydroxyl group on a carbon. What are we reacting with? Thionyl chloride. Thionyl chloride alcohol, you replace the hydroxyl group on the carbon with the hydroxyl group with a chlorine. Everything else, my R group stays the same. This stays the same. Here's my carbon with the hydroxyl group. It's now got a chlorine. Oh no, we lost them. Next page. And if we look at N, I'm reacting with HBr. What is N? What functional group is here? Hydroxyl group on a carbon, alcohol. Alcohol plus HX. I didn't write it there. I should have. Bad, Dr. White. X can be chlorine, bromine, or iodine. The carbon with the hydroxyl group will now have this halogen. So you have 4 carbons. You don't break carbon-carbon single bonds. You replace this hydroxyl group with bromine. Let's go up to M, which is here. And I played the chemistry instructor's favorite trick on a test. And that is put a big, scary molecule. Because if you don't look for a functional group and know your general reaction, that's a big, scary molecule. If you know to look for a functional group and know your general reaction, it's just a molecule. And if we look, what's different? Carbon with the hydroxyl group reacting with HCl, HX. What happens? You replace the hydroxyl group with the halogen on the carbon that the hydroxyl group was on. This one. Do you break carbon-carbon single bonds? No. And therefore, this stays the same. Redrew it, comes along for the ride. The only thing that changes is the hydroxyl group is replaced with the halogen, in this case, chlorine. And I realized, and Doc, don't tell anybody, shh, Dr. White was too lazy to re-alphabetize everything. So I popped another Zayseth's rule problem on the end. Let's go through it. Here I have an alcohol, acid and water. General reaction is alcohol with a carbon with an adjacent hydrogen, sulfuric acid, H2SO4, heat. You get a double bond, you lose water, it's called dehydration. And here, Zayseth's rule tells you get the alkene double bond with the most carbon atoms bonded directly to the carbon atoms of the double bond. Well, if I lose a hydrogen from A in the hydroxyl group, I'll get this compound. If I lose hydroxyl group and hydrogen from carbon B, I'll get this one. Now, if you notice on A, what carbon atoms are directly bonded to the two carbons of double bond? This one and this one. If we look at B, here's my two carbons of double bond. What carbon atoms are directly bonded to the carbons double bond? This one and this one. And students forget this one. Dr. White didn't. Count the circles, 2 here, 3 here, which is a larger number, 3. B is what Zayseth's rule will teach you, you will get. And that's everything you want to know about alcohols. We're afraid to ask. Any questions? It isn't cut class Wednesday, is it? I think I spoiled you guys, a lot of them, by putting my videotapes up, but it also helps. All right, let us get back to ketones and aldehydes. Just to remind you, I better check when I don't. Everybody see the whiteboard and this says cyclic, no number on? Thank you. When you have a carbon, double bond to oxygen, it has a hydrogen R group, which means carbons and hydrogens. We call this an aldehyde. When you have a carbon double bond to oxygen, and now instead of, push the wrong button, that's what happens when you have big fingers, and the pen I use you have a carbon double bond to oxygen with two chains or R groups, R and R prime. Remember, this is like X and Y. This means they can be the same or different in number of carbons and hydrogens and other things too, but for now, let's keep it that. And this is called a ketone. And as I went through Monday, you find the longest chain with the carbon double bond to oxygen, which is called the carbonyl carbon. Drop the E when you name the longest chain, including this carbon, as an alkane. And add Al. Now, one of the things I forgot to mention on Monday, alcohols are OL ending, aldehydes are AL. Make sure on test and the final, when you write an aldehyde or an alcohol, make sure it's clear it's OL or AL. You don't want me guessing, because I can be 50% wrong. And for this, remember, no number. Because an aldehyde, the carbonyl carbon is always 1. They rock. Now, ketone, Find the longest. Now, aldehydes can't be in a ring. Ketones can. So find the longest chain the carbonyl carbon, the carbon double bond to oxygen is in, or the ring. Name it as an alkane or cycloalkane. Drop the E, then add O-N-E. And for acyclic, need a number. And for cyclic, no number, because the carbonyl carbon is always number 1. That's always good to do a quick review. And finally, one of the most important things I can teach you this semester, at least for me personally, is this. Carbonyl group. Carbonyl group is carbon atom double bonded to an oxygen atom. You should know how to draw the carbonyl group and how to describe it with words. I go for a 5. I haven't done that ever. So it's really important to know what the carbonyl group is and how to describe it, how to draw it up here, how to describe it with words, carbon or carbon atom, double bond to oxygen or oxygen atom. Either way works for me. All right, let's get back to where we were. Now I did a quick little review. Monday, I finished up just starting to talk about Friedel Crafts acylation. Remember, and I'll never ask on a test, but this is called an acyl group. How that got that name, I don't know. And it's part of certain functional groups. And it does contain a carbonyl carbon. And notice you put this on a benzene ring, and that's why this is called acylation. So if you take a benzene ring, and this is an acid chloride, and react it with aluminum trichloride, you replace one of the hydrogens on the benzene ring with the acyl group. If we look at this reaction, I'll do this, I already started to. If I react this, what do you get? Well, what's the general reaction? Oh, that's a benzene ring. Look for what's different. That's an acid chloride, which unfortunately is the only time I'll get to talk about these very interesting molecules or functional group. Aluminum trichloride. And I made this special type we call, R prime, an aromatic ketone. So if I look up here, I say, well, benzene ring, what's R? Because this is my acid chloride ethyl, aluminum trichloride catalyst. What's R? 2 carbons. You don't break carbon-carbon single bonds. And that's what you get. And why don't you have some fun and try this reaction? What do you get when you react this compound with this compound in the presence of this compound? Go. All right, is everybody done? I guess so. Nobody's screaming at me. All right, let's do it. What do we have here? Benzene ring. Ooh, what's different? Carbonyl with a chlorine in our group and acid chloride. Aluminum trichloride catalyst, and we get an aromatic ketone. What's my R group? Isopropyl. So I'm going to have my benzene ring. Don't forget to put the lines in. Carbonyl. What's my R group? Isopropyl. And that's how you do. Oh, let's do one more. These are fun. And why don't you try this one for your fun and enjoyment on this windy, was sunny afternoon, fall afternoon. You can tell it's fall. A lot of the leaves around my house are falling. Oh, is that bad? All right, when you're done, give me a thumbs up. All right, I think everybody's done. Well, in that case, I better get to work. All right, what do we have? Ooh, a benzene ring. Wait a second, we got a benzene ring here, but we have here an acid chloride. In this case, this is my R group. React it with aluminum chloride. And what do you get? an aromatic ketone, where one of the sides on the carbonyl of the ketone, remember carbonyl, carbon oxygen, double bond, is an R group and one is a benzene ring. In this case, oops, drew it too low. Let's start over here. That's better. And this would be the compound. Now let's take a look at this compound. Notice it's a ketone. In this case, both R prime and R are benzene ring. And this is called benzophenone. That's a common name, not an IUPAC name. Now, one of the things I've been doing more and more, now is the time for me to do it again, is remind you, you should ask the question, why am I learning this stuff? And the obvious answer for you to answer is, because I want to get into the program or school that requires me to take organic chemistry and get a good grade. But why learn organic chemistry? Well, let's look at the reaction you just did. And that's this, take benzene, and this is called benzoyl chloride, react it, you get benzophenone. So what? Well, it turns out you've probably used benzophenone. No, I never did. Yes, you did. That's the key ingredient in suntan screens and lotion that protects your skin from UV radiation. And I don't know about you, but I don't like getting sunburn. And you put that on that protects your skin so you don't get sunburn, and also so you don't get cancer, skin cancer from the harmful UV radiation of the sun. How does it do it? All the double bonds and the rings that are called in conjugation with the carbonyl carbon, it can absorb ultraviolet radiation. I'm not going to go into how it actually does it in this class, but it's due to the p orbitals or pi orbitals and various energy levels, but it can. Now, aromatic ketones also play an important role in what's called the initiator in what's called photochemistry. And photochemistry is when you shine light on something, it undergoes a chemical reaction. And where will you see that? Well, if you go to any, well, now it's getting a little outmoded, but if you go to any place where they make print newspapers or do other high-speed printing, they put the ink on the paper in a certain way, and it goes under ultraviolet light and immediately cures the ink. Now, where you have probably seen photochemistry, organic photochemistry, didn't realize it is, how many of you have seen when you, and I don't, obviously I forgot to do my nails, but you put your nail polish on the newer stuff, then you hold your nails underneath a light. Hold it underneath a light, but not a regular light. It's a UV light. And what is that doing? That has an aromatic ketone that absorbs it, the UV energy, passes it along to the reaction that makes a polymer. I'll teach you later about polymers that hardens the nail polish on your nails. I think most of you have seen that. You go into a place where you put your hands under the light to cure the nail polish. That's very sophisticated organic chemistry. But you didn't even know that. Now you do. All right, that's how you make ketones and aldehydes. Let's go back and look at the carbonyl group, part 2, because we already did one. Now, oxygen, and the switch is off for this slide, but this is good background information. What I mean by switch is off, this won't be on a test or the final, but still good background information you should know. Oxygen is more electronegative than carbon. What does that mean? When they're sharing electrons, oxygen is bigger and stronger and says, let's share them a little closer to me. Carbon says, okay. And the pi bond of the carbonyl, it's a sigma and pi bond, remember it's a double bond, is polarized. See board. Well, guess what? I can write on my slides, so I will. Here's the carbonyl. Now, because this oxygen is more electronegative than the carbon, there's a slight negative charge on the oxygen and a slight positive charge on the carbon. Not a full charge. Now, in chemistry, this means difference, capital delta in the Greek language, alphabet, and small case delta means little difference or slight charge. And that means nucleophilic attack, warning, fancy new word time, attack, and by the way, organic chemists are violent. We use terms like attack instead of reacts, and actually in the literature, you'll read that, occurs at the carbonyl carbon of the carbonyl group. So a lot of the chemistry occurs at that carbon because something that's looking for a positive charge, nucleophile, philic comes from the term phile, meaning loving. Nucleo comes from the nucleus, which is positive charge, and a nucleophile is something that loves a positive charge, which is the carbonyl carbon. And nucleophilic addition to the carbonyl group, nucleophiles attack the carbonyl carbon group at the carbonyl carbon. As you can see here, this arrow shows you the nucleophile is going to attack there, and the electrons here from the pi bond go to the oxygen. This is one case. Nu is shorthand for nucleophile. The pi bond is broken, and a new sigma or single bond is formed. Now, sometimes it may be where nucleophiles of this form, and what you'll get when this attacks this, and this the switch is off, you form this. This is a conjugate base of an alcohol, or conjugate base of an alcohol, which is very strong based. I add acid to it, which comes from the nucleophile, Nu minus H plus, like HCl is the H plus Cl minus. And a lot of the reactions, not all of them, in ketones and aldehydes, you'll form an alcohol. I have everybody's attention. Everybody, breathe in, let it out. Breathe in, let it out. Are you nice and relaxed? Stay that way. The next reactions are probably four of the hardest reactions I'm going to teach you this semester for students. Relax, take a deep breath, let it out. Are you relaxed? Let's do it once more. Let it out. So if you have a little difficulty at first, yeah, you're going to, because most students do, but you'll learn it. So those are next four. Because they're challenging, the next four reactions, I will never, ever put a synthesis problem on a test or a final. That's not fair. And I think at least as of today still, what time is it? As of about 1:47, 1:46, the Supreme Court still has outlawed cruel and unusual punishments to students by instructors, so I won't. But anyways, relax, we're gonna go through, it's interesting reactions. All right, the first one is formation of a hemiacetal or hemiketal. And I have it written here, and actually a better way to write it is this. When R prime is hydrogen, it's an aldehyde. When R prime is carbons, it's a ketone. So either aldehyde or ketone reacts with, and I'm using R prime and R double prime, just like XY. And now we have a third one, Z, and that's why we use primes. An alcohol, and you need acid catalyst, usually sulfuric acid will do it. Other acids will also. And what happens is, keep your eye on the carbonyl carbon, because that's where all the fun is. What's attached to it stays there. So I'm going to draw my carbonyl carbon. This part goes to the carbonyl carbon, and this hydrogen goes on the oxygen from the carbonyl carbon to form this molecule. Now, this is a natural functional group, which I don't want to ask you to learn nomenclature, even though there are. Now, when R prime is a hydrogen, I won't ask you to know the name, but other classes, it might be interesting for you to know, that's called a hemiacetal. When R prime is alkyl, meaning you started with a ketone, this is called a hemiketal. And again, let's go through it. When you're doing reactions with ketones and aldehydes, most of the fun, not all, but 99% of it, 97%, happen at the carbonyl carbon. The carbon double bonded to the oxygen. What's attached to it stays attached to it. Here was the carbon that was the carbonyl carbon. And this alcohol, think of it as a nucleophile, Nu minus H plus. You break the pi bond, the OR goes to the carbonyl carbon, or what was the carbonyl carbon, and the oxygen from the ketone or aldehyde gets the hydrogen. If I look at the clock, it's time for our break. I'll see you in 5 minutes. I can go stretch. And I'll see you in 5. I'm back. All right, everybody back? Let's get going. Thank you, JC. All right, I was talking about formation of hemiacetal, hemiketal. And if you start with an aldehyde or ketone, react it with an alcohol and acid, you get this compound. When R prime is H, that's called a hemiacetal. When R prime is carbons, alkyl, it's a hemiketal. I'll never ask you what's a hemiacetal, hemiketal, but I'll use the terms in class, so I better define them. And let's look at the reaction. Now we're getting into some really juicy chemistry. And the question is 3 points, give the organic product or products that are following. Well, what do? Well, you look at each molecule and notice here what's different. Oxygen, double bond to carbon, carbonyl, hydrogen, and carbons, that's an aldehyde. Well, in this reaction, when R prime is H, it's an aldehyde. If it's carbons, it's a ketone. Ooh, what's different here? Hydroxyl group on carbons, this is an alcohol. And we're having it react with acid catalyst. And what you get is, keep your eye on the carbonyl carbon, because that's where the fun is. What's attached to it, R prime and R double prime, are still attached to it. From the alcohol, oxygen, R. By the way, the carbon with the hydroxyl group of the alcohol is the carbon with the oxygen in the hemiacetal, hemiketal. And you get a hydroxyl group. And this was the carbon that was the carbonyl carbon. So if we look over here, I'll call this R prime. I'll call this R double prime. And on the alcohol, this is R. So I'm going to draw this carbon. What was the carbonyl carbon? This right here. What was attached to it up here is still attached. H, my R prime, and this should be a double prime. And my R double prime, which is a methyl, sometimes I've got R on the brain. My methyl, then I'll have an oxygen. What's R? Ethyl. And that same carbon will have this. And that's how you do it. Your turn. And there you go. Have fun. By the way, we're getting into the real good stuff now in organic chemistry. All right, give me a smile or a thumbs up when you're done. I think everybody's smiling or thumbs upping at me, so I better get to work. All right, let's take a look at this reaction. And the question is, what product or products do you get when you react these two compounds together with acid catalyst? Well, what's different? Ooh, carbon double bonded to oxygen, carbonyl. And on that carbon, I have a methyl group and an ethyl group. I'll call this our double prime, doesn't matter which one you call which, but I'll do this. And in this case, I have a ketone. Now, this could have been hydrogen, and it could have been an aldehyde, but it's not. What's different here? Ooh, carbon with the hydroxyl group, alcohol, acid catalyst, and I know, keep your eye on the carbonyl carbon, because that's where the fun is. What's attached to it, our prime and our double prime are still there. This OR from the alcohol is bonded to what was the carbonyl carbon, and this becomes an alcohol, or actually an acetal. It's not really an alcohol, the hydroxyl group on there. So if we come over here, R is methyl, R prime is methyl, our double prime is ethyl. So I'm going to keep my eye on the carbonyl carbon, redraw it. What's attached to it, R prime, methyl, our double prime, ethyl, are still attached. This tells me I have an oxygen. What's my R? Methyl. And I have a hydroxyl group, and that's how you do it. Oh, let's do one more. And now, have some fun. Your turn. Oh, forgot something important. This would take forever and a year if I didn't put it in my catalyst. Remember, a catalyst is something that is not consumed, but makes the reaction go quicker by lowering the activation energy. Important thing is it makes it go quicker. So instead of waiting 2 months, it's done in a couple hours. That's quicker. I see one person's done. I see 2 people. I assume number 3 is done. We got a personal class today. You got me. Almost all to your very own. Aren't you lucky? Well, that's what happens when I spoil people with YouTube videos. But let's do this. Now, let's look at this first one. Ooh, oxygen. And it's double bond to carbon right here. There are carbons here and here. And guess what this is? This is a ketone. It could have been an aldehyde, but it's not. And just so happens, R and R prime and R double prime are connected together in the ring. What's here? Carbon, carbon, carbon. Hydrox group on a carbon. Alcohol. Acid catalyst. What do you get? Keep your eye on the carbonyl carbon because that's where the fun is, really is. I'm going to draw that carbon, what's attached to it, carbon-carbon single bonds. You don't break. And then hydroxyl group. And then OR, the R comes from the alcohol. Well, if we look here, this is my R double prime, this is my R prime, they're connected together. So guess what? I still have the ring. You don't have to do this, but I will. Here's the carbon that was the carbonyl carbon. What happens to it? You break the pi bond and you have oxygen. What's R? Well, N-propyl. And then on that carbon, we'll also have the hydroxyl group. And that's how you do it. And that's how you make a hemiacetal or hemiketal. Now, the next reaction is similar but different. And that's the formation of an acetal or ketal. And I better check because I haven't in a while. Everybody see that on the screen? Thumbs up, people. Thank you. Well, you guys got the fastest thumbs up this side of the Mississippi. Thank you. And probably the other side too. All right, let's look at this. And my software doesn't like to put the carbonyl carbon in. I sometimes forget, so I'll write it again for you. If you take an aldehyde or ketone, when R prime is H, it's an aldehyde. When it's carbon, it's a ketone. And now we reacted not one, but 2 molecules or moles of an alcohol, acid catalyst. What happens? Keep your eye on the carbonyl carbon. What's attached to it is still attached to it. And now both of these are bonded to the carbon that was the carbonyl carbon. When R prime is H, it's called an acetal. When R prime is carbon, it's called a ketal. Now you know why the previous one, hemi meaning half acetal, half ketal, because you didn't have 2 OR groups on there. So let's look at an example. And the question is, what's the organic product or product for the following reaction? I'll do this one. We come over and look at this molecule. What's different? Ooh, oxygen double bond to carbon. Carbon's here, carbon's here. It's a ketone. Now, it could have been an aldehyde if R prime, which is a methyl, was a hydrogen, that'd be an aldehyde, but it's a ketone. Ooh, 2 of something. What? Carbon, carbon, hydroxyl. It's an alcohol. Acid catalyst. Keep your eye on the carbonyl carbon. That's where the fun is. I'm going to redraw that. What was attached to it stays attached to it. Again, these are challenging reactions. And then on there, I'll have from each alcohol the OR group. And when you lose this oxygen and 2 hydrogens, you also get here, which Dr. White doesn't put in organic stuff here, water, but you don't have to put that down. So if we look up here, I'll call this R prime and R double prime, and they're the same. And over here, that's R. So keep your eye on the carbonyl carbon. What's attached to it, R prime. R double prime is still attached to it. If we come down here, that carbon will have two oxygens. And what's on the oxygen? R. And in this case, what's R? Ethyl. In this case, wow, it's a big fancy molecule, yeah. And that's called a ketal, but I won't ask you that. It's your turn to have some fun. And the question would be, what's the product or product for the following reaction? I see one done, possibly two done. And I'll assume number three, are you done? I guess so. Yes, you're done. Thank you for letting me know. So my star pupils are all done. And let's take a look at this. We look at this. We look at the first molecule. What's there? Ooh, carbonyl. Carbon, double bond to oxygen. Look for what's different, what's not hydrogen, what's not oxygen. That'll tell you where the fun is. And notice we have carbonyl with a hydrogen. It could be R prime, but in this case, R prime is hydrogen. And we have here carbons. I'll call that R double prime. Ooh, look, two of something. Carbon with a hydroxyl group. It's an alcohol, an acid catalyst. And what do you get? Keep your eye on the carbonyl carbon. What's attached to it is still attached to it. When I say either hydrogen or carbon single bond. And then I'll have two oxygens. And then from the alcohol, the R groups. So in this case, here's R prime, here's R double prime, and here's R. In this case, X, Y, and Z are all the same. Well, that's okay. Actually, I did that wrong. Let's try it again. I had ketone on the brain. That's R double prime. That's R prime. That's R. So keep your eye on the carbonyl carbon. I'll redraw that. What's attached to it? R prime, which is hydrogen, R double prime, isopropyl. See, Dr. White wasn't lying to you. I don't walk on water unless it's ice. Then this carbon will have two oxygens, and the R group on there is methyl. Oh, let's do one more. And this is a cyclohexane ring, not a benzene ring. Well, I think I lied and told you these are hard reactions. You guys are getting the hang of it. All right, I think everybody's done. And they're giving me like, come on, get to work. Everybody done? Yep, thank you. All right, we look at here, what's different? Ooh, Carbonyl Group, the oxygen gave that away. And here, carbon-carbon hydroxy group on alcohol. So I have a ketone here. Notice I have carbons here and carbons here. This could have been a hydrogen. It could have been an aldehyde, but it's not. I'll call this our prime, our double prime, and ooh, 2 of an alcohol, acid catalyst. Here's my R group. And keep your eye on the carbonyl carbon, because that's where the fun is. What's attached to it, R prime, or it could be a hydrogen, and our double prime from the ketone or aldehyde is still attached. You get 2 oxygens, and then on each oxygen from the alcohol, the R group. So if I come here, here's my carbonyl carbon. I'll draw that first. What's attached to it, R prime, methyl. R double prime, cyclohexane ring. 2 oxygens. Notice 3 carbons. The N carbon has the hydroxy group and propyl. And there you go. You have this ketal. Now, I've said I'd be doing this more often, and Dr. White doesn't lie. You should always be asking yourself, why am I learning this stuff? And you know the obvious reason, because you want to get a good grade. For a course, you need this for a program you're trying to get into, or college or school you're trying to get into. Well, why learn this stuff? Well, the last 2 reactions are the reactions Mother Nature uses to make all the carbohydrates in our life. She uses both of those, and later when we get into carbohydrates, I'll show you exactly how she does that. But as you know, Mother Nature is the greatest of all our organic chemists. And if it wasn't for those 2 reactions I just taught you, making hemiacetal, hemiketal, and also making acetal and ketals, we wouldn't have any of the carbohydrates in our life. Is that sad? No potato chips, French fries, potatoes, rice. What you don't know, but I do, and I'll teach you later on, we wouldn't have any trees, we wouldn't have any plants, you wouldn't have any grass to cut or look at. All that would be gone. We'd probably be gone too, because we wouldn't have carbohydrates in our planet, which would be pretty devastating. So why are you learning these things? Because these make molecules that are important in our daily life. And with that, it's time for our lab. Everybody get your lab coat on, your safety gloves, your gloves on, your safety goggles on. Okay, let's go. And this is available for you to download from D2L. And today's lab, everybody see aromatic electrophilic subs, thank you, is aromatic electrophilic substitution. Now, if we're in the lab, I'd be warning you about the dangers of sulfuric acid, concentrated nitric. This is one of those where I teach you how to handle some very hazardous chemicals safely, which students do. But you have to be very safe with this stuff. I had one student at the other school got some on his arm, and it left a very bad burn. They call it an acid burn because it looks like on your skin, if you put a piece of hot metal on there and burns it badly, that's what it looked like. And because of that, after that accident, I made sure always in my lab, usually I don't, but for this lab, you'd have to wear a long sleeve top or a lab coat to protect your skin, along with gloves, which the school provides. All right, let's look at this lab. Now, in electrophilic substitution, we replace one of the hydrogens with the electrophile. Electrophile is something that loves electrons, and all these pi electrons in the benzene ring attracts an electrophile. Now, what if there's something on the electrophile, on the benzene ring? And for some reason, for benzene, I don't know how it evolved, but all organic chemists do it, I do, we have a Z group, and that's called a director. And a director tells the electrophile coming in where to go. It can go 1, 2, which would be ortho. It can go 1, 3, which is meta. And it can go 1, 4, which is para. Now, it turns out there are only 2 types of directors. Either ortho-para or meta. So you either have a Z group as you get ortho-para products, or Z could be a meta director, you get meta. Now, once in a while, when Z is very large, it blocks off the ortho position. So even though it's called an ortho-para director, you just get para product, but it's still called an ortho-para director. Again, there are 2 types of directors. One is called ortho-para, the other is meta. Now, the Z group is a director. How many of you have ever gone to a large concert or some county fair? Like, I used to go to the one in Kane County, but I haven't in ages because of the internet. You can buy most of that on the internet anyways. But they would take an open field and make it into a parking lot. And they have those people who are nasty. They don't like me. Maybe that's why they're nasty, because I don't listen to them. And they direct you. No, don't park there. We want you to fill up this row. Go all the way down. No, I want to park there. No, fill up this row. And the Z group on a benzene ring is like a director. It says to the group coming in, no, you go here or here or here. And there are 2 types of directors, ortho-para or meta. Remember that, 2 types of directors. Now, sometimes if Z is real big, it blocks off the ortho from the electrophile coming in, because it's just called steric hindrance, which I really don't teach in this class. It's just blocks it off. You can't get in there. I'm big. But it's still called an ortho-pair director. Important. Remember that. Now, in this lab, if we're in the lab, you'd actually be doing this. You're going to start with bromobenzene, and the director here, Z, is a bromine atom. And you're going to react it with nitric and sulfuric acid. Now, there's something I must show you. Why do we react nitric and sulfuric acid together? On a test, I'll never ask this, but you should know this for the lab. Sulfuric acid, think of this as H+. Nitric acid, HNO3, I'm going to write this way. Now, it turns out this is attracted to the oxygen and forms this intermediate. Which has a plus charge. Now, normally if we're in the lab, I'd be writing this on a whiteboard and I'd use my hand, but I'll do it now. Little red dots. If I forget about the nitro group and look what's in the red dot circle, I see, oxygen and 2 hydrogens. Oxygen and 2 hydrogens. OH2. Wait. H2O, water. And whenever you have a stable leaving group, something that can leave from a molecule as itself a stable molecule, it does. It says, goodbye, I'm out of here. And it loses water and forms this called the nitronium ion. And you notice it has a positive charge. And it doesn't want to be with a positive charge. It's looking for electrons in the worst way, and it attacks the benzene ring and replaces one of the hydrogens with NO2. That hydrogen comes off as H+, so you get this back. So this truly is a catalyst. Now, you notice the reaction up here? I don't show you where the nitro group is. Is it in the ortho position? Is it the meta? Or is it the para? Why? Because I don't want to give away today's lab. And what you would be doing in the lab today is first mixing these together to make this, then adding the bromobenzene slowly, then you heat it for 30 minutes, and you'll get a solid. And in the lab, I'd show you how to use a Buchner funnel. And I have some videos for you to look at how to use. And a Buchner funnel is a way organic chemists separate a solid from a liquid. Now, this is a solid, bromonitrobenzene, whether it's ortho, meta, and para. So to find this identity, what can you do? Take the melting point. And that's what you would have done. It's sad you're not in the lab. It's an exciting lab, very exciting. Dangerous, but exciting. And notice I have warnings all over the place. Now, for this lab, I'd ask you to look at least the first video. Second one's similar, and third if you're into it. And here's the procedure where you heat up some water, because you'll be needing that. In a round bottom flask, you'll add the 3 milliliters of concentrated sulfuric. Then you'll cool it down in what's called an ice water bath. And then, because it's an exothermic reaction, it gives off heat, and you don't want it because it messes it up. And very slowly, with an eyedropper, with swirling, you'll add with a glass funnel. That's what happened when the student had his accident. he was adding nitric acid with an eyedropper and he didn't have the glass funnel, I wouldn't even try and do it without it, and obviously had his accident. When you see me during this lab, I'm at DEFCON 1. If you don't know what that is, that's the government's different levels of readiness for our atomic bomb forces. DEFCON 1 has been described as you have a gun in your hand, you're pulling the trigger, the hammer on the gun is all the way back, just about ready to go forward. I'm at high security. I'm keeping my eyes on everyone at the same time. I do it. For me to do this lab, I've dealt with dangerous things, but to make sure all students do it safely, it's high stress time. But we do it. After you add the nitric acid, you wait 2 minutes, then while it's still in the ice bath, you'll add your bromobenzene, 1 portion, let it sit for a while, let it come to room temperature, because you don't want to put something cold directly in boiling water. You could, but I don't like to. And then you heat it. Now, there's a side reaction that goes on. If I don't tell the students, they get scared really bad because something, all of a sudden, you're in a fume hood, so it's safe. But this brown smoke starts coming out of the top, reddish brown, and it's nitrogen dioxide, which is quite poisonous. But you're in a hood, you're safe. After 25 minutes, you take it out of the boiling water. You let it cool. You put it into this is the one I don't teach you about, into ice water, and you'll see a solid. Because it's ECC, our labs are an hour and 50 minutes. This is about 2 hours and 20. You don't have time to isolate the salt and do the melting point. So I tell you that, and then afterward you clean up. And you notice since everything's acidic, very dangerous to your skin. I'll teach you later in the semester why acids are dangerous to your skin. It's an organic reaction. We use gloves. All right, now, I would come around and say, show me your solid, which everybody gets one. It's like falling off a log, this lab is so straightforward, it always works. And this is my initials, K inside a W, that I developed my freshman year of high school. Oh, by the way, story time, I have time. We'll get out early today. Back when I was a freshman in high school, we had to take non-Western civilization, and the teacher was boring. And I'd be doodling, looking out the window, and he'd think I was never listening to him. I was, but I was still bored, trying to keep myself from falling asleep. I always got the highest scores in the test. And the highest score, and he was upset because he always thought, are you cheating? No, I just wasn't paying, I didn't have to pay attention. Well, one of the things I did was that whole semester, I finally realized about a week or two, I need a monogram. And I finally developed one, and I've been using it ever since, as you see. It's a W, my last name, with a K inside of it, which is my first initial, and that's a KW. Yay. Now, I would tell you the melting point is 121 to 123. Now, most students, when they're doing melting points, usually get temperatures a little lower than the literature value, actual value of a product. Never higher, but usually lower. And as you learn from lab number 1, if you have impurities present, that can make your temperature lower too. So one of the things you have to do is right in here, you have to write in the identity of the product. And here are your 3 choices: orthobromonitrobenzene, metabromonitrobenzene, and para. And here are the melting points of here. Don't forget, this is the melting point you would have gotten. Don't yell it out now. And then you have to do these questions. Remember, this lab is due next Wednesday by, I think I'm putting down now 5 p.m. You have all this week and the weekend. If you have any problems, always feel free to come to my office hours on Monday and tonight, Wednesday night, from 6 to 7:15 in Zoom. If you ever need extra help, let me know and I can find some time when we can meet on Zoom, because I don't have to, excuse me, hold on, water time. If we are come at ECC, I only have my office hours when I'm there, which is Monday, Wednesday after class. But now you can catch me anytime because I don't have to worry about driving to ECC. We've got Zoom meeting. All right. Don't forget to hand the lab that's due today, do the practice problems. On Monday, I'll go through the epoxides and ether problem set. And I think that's about it, except one person I'm going to send a message to. And with that, I'm going to say goodbye. I love this. Gehen gesund, be healthy. I'll see you on Monday. Have a great rest of the weekend. Stay warm. It's getting colder out there. And we're done.